Okay, so here's where we were last time. There we go. Okay, here's where we were last time. Well, here's where we're picking up where we left off. So we're going to talk about flux through a curve. Now, we've talked about flux before. It was in a different context. It was where we had, in a three-dimensional context, and we had a flat surface, and we were interested in understanding as a fluid flows through that surface how much volume of fluid per unit time goes through that surface. We're going to do something totally analogous here, but one dimension down. So in 2 dimensions, not 3, through a one-dimensional flat curve instead of a 2-dimensional flat surface. And we're going to be interested in the area per unit time. It seems weird to say, but still quantity appropriate to the context per unit time of fluid that's passing through this now curve instead of a surface. Okay, so it's a nice exercise that I'm going to leave to y'all to persuade yourselves that this is the right formula. So the way you're going to get this is by looking back in Chapter 3 and seeing how we derived the formula for flux in the three-dimensional context, and you're going to pretty much rip all that off. It's just adapted appropriately, and of course it's area instead of volume, and blah, blah, blah. But it's extremely analogous, and like I say, nice exercise. As always, when I make these suggestions about things that you can work out for yourselves, if you get stuck, come talk to me. Happy to help. Okay. That said, I do think the formula is pretty believable as it is. I mean, after all, F dot n, just like in the previous formula, the Chapter 3 formula, and now length instead of area, but in both cases the size, appropriate to the context, the size of what we're interested in, how much fluid is flowing through. Okay, so pretty believable. All right, so now here's a related idea, boundary flux. We've talked about the idea of a boundary previously, if I can get that to it. Okay, so if I have a region, something like that, and again, I don't want to draw the whole thing. There's no need. I just need to draw one sort of small piece of it. Here's what the boundary looks like. Right? And by the way, we have a convention on boundaries. The convention on boundaries is that the direction along the curve is like so, again, with the region on the left. By the way, this is an example where thinking of it as move such that the region on your left is actually a little bit more geometrically clear than this idea of clockwise, counterclockwise. In particular, it should be counterclockwise because we can't see the whole curve, right? So it's not immediately clear which way is counterclockwise. So anyway, region on the left. Okay, now when we talk about boundary flux, this is a new idea here. When we talk about boundary flux, again, there is a standard convention. It is arbitrary, but it is standard, and so we're stuck with it. Again, for better or for worse, I think it's better anyway. The convention, when you're talking about boundary flux, the normal vector that we look at is the one that is outward. So away from your solid, not into your solid. Coin flip could have gone either way, I suppose. This is the standard, and again, stuck with it. Okay. All right. So how would we calculate all of the boundary flux? Now, I am going to, very first thing I'm going to do here is I'm going to scratch off that just for a moment. I'm going to scratch off all of this. We'll come back and look at that in a minute. But for the moment, I just want to focus our attention on just one little piece of our boundary curve here. Let's see here. Let me go back to this size. We will look at... we're going to look at this little bitty piece of boundary curve like that. Of course, there's a lot of these little pieces along the entire boundary curve, but looking at this one little piece, we have a piece of curve of a given length. We have a normal vector telling us which direction is the correct direction, the positive direction through this piece of curve, and we have a vector field describing, let me get rid of my stuff down here, vector field describing the fluid flow that I want to compute the flux of through this little piece. And I'm just going to immediately write down the formula for it, and it is right here. This describes, describes the amount of flux through this little bitty piece of curve. You'll notice using the formula pretty much from the previous page, right? If this is a little piece of curve of length ds, then that's your length right there. Okay. All right. And now, of course, that's just for that one little piece. We want to add up over the entire curve and thus integral to add up over the entire curve. All right, is everybody on board so far? So now we've got a new kind of an integral then to deal with, and this is a little bit unsettling at first glance. You look at this integral that we are staring down the barrel of here. We've never seen one of these quite like this before. Just a little bit different. We've seen it with a t here. T being the unit tangent vector. This is a normal vector. It's very different, right? So how are we going to sort of adapt that? And this is where the other stuff that I have on the that I've scratched out is going to come in really handy. And it goes like this. Let's look at, again, f dot n. There's f and there's n. Okay. Now, next, I'm going to pull a soon-to-be-seen slick move, and I'm going to take both of these vectors, and I'm going to rotate them 90 degrees counterclockwise, just to see what I get, right? So I'm going to rotate f, for example, 90 degrees counterclockwise. F has coordinates p comma q, and flash back to linear algebra and remember all this business about rotations, linear transformations, matrices, etc. 90 degrees counterclockwise, turn pq into minus qp. Again, make sure you're good at that. If you're not 100% clear on how that works, come talk to me. I'll be very happy to help you out on that. Okay, so neat observation further, though, if I have an outward normal, that outward normal, if I turn it 90 degrees counterclockwise, becomes the correct tangent vector, right? Because, again, outward turned counterclockwise, and then if you look to your left, then you're looking inward toward the region. All right, so nice punchline I claim then that this green dot product, f dot n, I'm going to make the assertion that that is equal to this blue dot product, not f dot n, but f perp, this rotated f, minus q comma p dot t instead of n. Now, why would those be the same? Why is the green dot product equal to the blue dot product? We'll just make sure to, remember what we know about dot products. And we have this geometric version of dot products where it's the product of the magnitudes times the angle between them. And here's the thing. These two vectors, when I rotate each of them 90 degrees, that doesn't change their magnitudes at all. It doesn't change the angle between them at all. And therefore it doesn't change the dot product at all. So really beautiful fact then that this green dot product is equal to that blue dot product. And that then allows us to replace this integral that we're not sure what to do with because it's completely different from anything that we've seen before. Allows us to turn it into this integral that we've seen a million times. We totally know what to do with this. Vector field dot TDS. Hey, cool TDS. That's nothing to it. TDS is dx. So this is very simply a vector line integral. So nice little move. Who cares? What's the benefit of rewriting this brand new kind of integral as a vector line integral? Well, because we have computational tricks for how to compute vector line integrals. We can pull back through a parameterization. We can, what else do we have? Ooh, we have Green's theorem. It's a theorem for computing vector line integrals. Now, of course, Green's theorem comes with the catch Green's theorem only applies if the vector line integral in question is around a boundary. And it is. Right? The whole premise of this is that we were interested in computing boundary flux. Right? So the flux through the boundary of a two-dimensional region. And, well, that's what we've got then. So immediate translation then by Green's theorem. The flux that I want, this weirdo sort of strange NDS integral, is this regular old plain old circulation, boundary circulation no less, which is a double integral of Green's operator. And now it's all just it's all downhill from here. Now we have a couple of little details we've got to work out. We do have to evaluate Green's operator. Don't forget Green's operator is the x partial of something minus the y partial of something, right? Easy to lose track, though, of the little specifics and particulars here. What do I take the x partial of? What do I take the y partial of? Don't rely too much on the character for character formula for Green's operator. dq dx minus dp dy, right? It's very tempting to say, well, the dq dx minus dp dy. But that's the formula for if you were taking Green's operator of p comma q, which we're not. Right? We're taking Green's operator of f perp. So really, when you think Green's operator, I mean, we all kind of have it memorized as dq dx minus dp dy. Just remember that it's really the x partial of the second coordinate. The second coordinate in this case being p minus the y partial of the first coordinate. In this case, minus q. Everybody happy? A little detailed devil there to have to worry about. Okay. And now it really is kind of all over but the celebrating. Just observe that this minus sign cancels with that minus sign, and then observe that this resulting integrand is familiar. That is, in fact, straight out of chapter 3. It's this thing called divergence. And sure enough, we have a nice compact answer. In fact, this is such a nice answer, we're going to call this a new theorem, that flux can be computed as a double integral of divergence over the interior. Really cool theorem. Let me point out one of the things that's really kind of jaw-dropper about this theorem. This original integral is a one-dimensional integral. It's computed over a curve. It's kind of a line integral. And yet what we've shown is that it ends up equaling to a double integral. Again, pretty creepy. How did that happen? Now, of course, a real easy answer as to how that came to pass, of course, the heavy lifting was done by Green's theorem, which, of course, is a one-dimensional integral that turns into a two-dimensional integral. So not really that surprising. But anyway, it remains that it's got the same surprising feature that Green's theorem has. Okay. All right. Let's see here. Moving along. Let's apply this. Here's a potential question. We want to compute a flux. Oh, I'm sorry. Yes.
So about flux.
Yeah.
I thought it was flow rate over an area. How could we say that it's like a small? Like,
Yeah. No, that's right. So we have this new idea that I'm claiming called flux through a curve, and I left a lot of that as an exercise, right? So just what you want to do is imagine that your vector field F represents a fluid flowing through, as indicated here, right? And now ask yourself, in a small piece of time, how much fluid, what would the fluid look like that has passed through this piece of curve in a small amount of time? It's going to give you a little parallelogram. Write down the formula for the area, and that's the area, not volume, because this is a two-dimensional fluid, right? But write down the formula for that area. details to be worked out, copycat shamelessly off of what we did in chapter 3, right? And if you interpret analogously, go through and do all the details, this is what comes up. Yeah.
So what physical quantity would it be? Like,
Yeah, sure. So let's imagine we have, I'm going to pick a fluid, two-dimensional fluid. I'm going to choose a herd of wildebeests, right? And we could talk about, how many, what the density of wildebeests is, and we could talk about the velocity of the wildebeests as they migrate or whatever, right? And then reasonable question I might ask, okay, I've got this line in the ground, how many wildebeests walked over the line, right? And this formula, suitably interpreted, would answer that question. Is that everybody happy with that? Okay. All right. Okay, so here we go. We're going to compute as requested this flux. Again, don't brute force these questions when you don't have to. This being conveniently a curve that is, let's see here, outward through the unit circle. Well, that's literally a boundary. Oh, whoops. Anyway, literally a boundary. So the question I've been asked is not just an arbitrary flux. It's a boundary flux. And being as it is a boundary flux, our two-dimensional divergence theorem tells us that this boundary flux is a double integral of divergence. So again, here's the heavy lifting right there. That's where the magic happens. Question about flux, specifically boundary flux. Snap my fingers, double integral will answer the question. And now, again, all details at this point. We do need to compute the divergence. Okay, fine. So we've got this vector field here. I'm going to have to figure out how to compute the divergence of it. I'm going to have the x partial of this, the y partial of that. You add those up. Pretty easy arithmetic is -3. Now we have an integral of a constant over a disk. Chapter 5 results, right? Factor out the constant, area of the disk, answer. Everybody all right? All right. Okay, now here's a different take. Let me remind you what we just did here. We got, here's our two-dimensional divergence theorem, and where did we get it from? Well, we got it by kind of letting Green's theorem do most of the work for us. So let me say that differently. We made sophisticated arguments, very sophisticated arguments about circulation. The fact that it's an accumulating quantity, the fact that there was an associated density, blah, 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 right? Sophisticated argument to relate circulation to a double integral. And then with the purple theorem here, I just kind of basically just, I can connect flux to this thing, and I can connect this thing here to double integral of divergence. This was a piggybacking off of the heavy lifting having been done by Green's theorem. So here's the thing. You don't have to do that. Boundary flux is on its own an accumulating quantity. We don't have to borrow from Green's theorem at all. Step 1, let me try to persuade you that boundary flux is actually an accumulating quantity. Again, if you have a hull area, here's what the boundary flux would look like. There's the boundary flux, if you will, of the hull. Now let's look at this left piece by itself. For the left piece, this is what the boundary flux of the left piece would kind of look like. It would be, computed over those edges with those orientations. Now we look at the right piece. And again, this is what the boundary flux would look like over just D2, just that right piece. Again, we find ourselves in this familiar situation of we need to know if green plus blue equals purple, right? Well, it is looking good over here. looking pretty good over here. Everything kind of matches up. The remaining question is what to do about this stuff in the middle. In some sense, the outward-oriented boundary flux that you introduced by cutting through the middle here, by creating a new edge, you might say, right there on this red curve. And so, well, we've got the green, we've got the blue. Notice that both of these little fluxes over this red line are over the same red line. The green one is oriented that way, namely, as is the standard, outward from D1. The blue one is oriented that way, again, according to the standard, outward from D2. These are opposite orientations. Let's see here. These are opposite orientations, and so they cancel. And so, indeed, everything checks out. And boundary flux is an accumulating quantity. Everybody all right? Now, I think it's worth noticing for your consideration, this looks a lot like the argument that I made when we were talking about boundary circulation. The big difference being that it's outward as opposed to along, right? Across instead of along. There was a lot of stuff that paired up automatically, but then there's this one piece that appears twice. This time, the oppositeness of the orientations is that it's the two opposite directions through. With Green's theorem, it was the two opposite directions along. Geometrically different. They're different quantities, right? But really analogous, very closely analogous, and morally kind of equivalent in a way. Done. Okay. All right. So with an accumulating quantity, you can talk about the associated density. There's a bunch of details to compute that associated density. That's just details. I don't think it's that important. What you will get if you were to go through and compute that density, yeah, it's divergence. Just like this already had us conclude. Okay, so it is its own separate accumulation theorem. So now, just real quick, I like to point out, just as a quick summary, I guess, of what we've seen and done concerning accumulation theorems. And I'm going to start here with the one that's extremely familiar. All right, I mean, this is the easiest accumulation argument. Mass. Of course it accumulates. If I have a pie and I cut it in half, I still have the same amount of pie. Right? I mean, it just could not be more clear. That's just how mass works. So the whole is the sum of the parts, like this. I can also talk about, for whatever the nature of the mass is that I'm interested in, I can talk about how much of it there is per unit area. Quantity, accumulating quantity per unit size. And accumulating quantity per unit size is a density. Is that cool? Old idea. We've done that a lot. Early chapter 5 kind of stuff. A real quick, last quick thought. We've got a lot of different kinds of densities in this class. We have to kind of sometimes specify, be more specific. What kind of density is this? And we name the density after whatever the accumulating quantity is that we're computing in the first place. Kind of the numerator, if you will, of the density fraction. So this is called mass density. Again, no surprise. Ditto population density. Same story. Different quantity, same story. So what's nice to notice is that these two, I like to call them accumulation theorems, or sometimes I call them density theorems. These two theorems follow the same pattern, the exact same pattern. It's just that now, instead of mass or population or something physical being our accumulating quantity, now it's these sort of more abstract little mathematical constructions. So circulation in this case, flux, outward-oriented boundary flux in this case, they are also accumulating quantities. And again, whenever you have an accumulating quantity, the whole point is that the whole is the sum of the parts. Right? And secondly, that any little piece is a corresponding density times size. And again, the pattern continuing. How do we name these densities? There's too many densities running around. Well, this is called circulation density because the accumulating quantity in question is circulation. And this one, big surprise, is called flux density because the accumulating quantity in question is flux. So I keep stealing from myself, right? There's a long and glorious tradition in math of stealing ideas and applying them elsewhere, right? Keep getting more and more good theorems coming out of the same ideas. Okay. All right, now real quick about the terminology. Obviously, this is an extremely common terminology. Mass density is practically ubiquitous, right? That's just what it's called. Heads up, flux density. This is not my creation. This is an extremely common term. This is such a common term that in my undergraduate physics days, again, a long time ago, sure, different university, fine, but still, that said, I heard this term flux density more than I heard the term divergence, namely what it's actually referring to. It's just really common, and it should be because it's so honest, right? Why do we care about this thing, this formula del dot? What does it do? What is it good for? It's literally a density where the quantity in question is flux. I don't know how to be more blunt, right, about coming up with a term to describe what this expression's job is. Its job is to be the density that helps me understand flux. So very common terminology, very natural terminology. You're going to hear it a lot. Be prepared for that. Okay, now that said, this one, for some reason, not as common, not as much use. Should be. I don't know why it isn't. There are other terms that get tossed around a little bit more. Obviously, Green's operator, curl, rote, right? We talked about a few of those a couple days ago. There's another one called vorticity, which is a really cool sounding word. It's great for intimidating people, right? I like it for that reason. But again, a little bit manufactured and hard to beat circulation density for bluntly clear as to what its job is. For your consideration. Okay, here we go. Next thing. I know y'all already know fundamental theorem of calculus, old news. I'm going to give you a different take on the fundamental theorem of calculus. So I claim you can view this as an accumulation theorem. Probably didn't think of it that way at the time that you first saw the fundamental theorem of calculus. But I make the observation that this formula describing a quantity that I like to call change is an accumulating quantity. And we don't think of it that way, or we thought of it as a formula. This is the way we compute integrals. It's a pretty common way to think about, why do I care about this expression? But I claim it's an accumulating quantity. So let me just scroll down here and use my diagram as kind of a visual aid. When I say accumulating, I mean it accumulates over intervals. Here's an interval on the x-axis. On this interval, some function that we're interested in, we have to have some fixed function f to talk about. Here's the total amount. I need to be able to draw a straight line. Here's the amount of change that happens on that interval. And now, okay, let me break this up into pieces. Let's talk about this piece here. That's part of my interval over which the function changes, I don't know, I guess about like that. Right, so there's the change that happens on the green interval. And then let's look at the remainder Remainder is about like this. The change on which is about like that. And now, for this to be an accumulating quantity, if I want to think of change as a substance, as a kind of a stuff that I can view as kind of distributed over the interior here, I would need for green plus blue to equal to purple. And yeah, of course it is. This is quite clear, right? No problem. I mean, it's very relatable. Does everybody buy it? All right. So change is an accumulating quantity. Having established that change is an accumulating quantity, then I can argue, as per usual, the whole is the sum of the parts. And on any part, I can talk about stuff per unit size and call that a density. So this is a pretty weird take on the derivative, right? Y'all have got several different ways of thinking about the derivative. We mostly tend to think of the derivative as being a slope, right? Calc 1 anyway, the derivative is slope. It's the easiest, sort of most obvious point of view that they give you on the derivative. Then eventually you see it as a velocity. And various other contexts, I've heard it described, I think very elegantly, as a sensitivity. If you change the input, how much does that change the output, right? That's pretty reasonable. And here, I'm giving you a whole new one, completely different take on what the derivative is. The derivative is what I call change density. It's this accumulating quantity called change per unit size in the domain. Now let me explicitly kind of talk through that here. Given a little piece of the domain, if I look at some little piece of the domain here, and I look at the corresponding amount of that the function changes over that little piece of the domain, the derivative is, well, it's the slope, sure. Rise over the run, fine. Blue over green, notice that being change, the green arguably being not a run but a size. We have accumulating quantity per unit size, and again, literally, that's a density. Right? So again, weird take on the derivative. Don't think of it any longer. Well, okay, let me not overstate it. You can still think of the derivative as a slope, right? But again, that's context dependent. But the particular perspective that's going to help us here is to think of the derivative not as a slope, but as a density. Okay. All right. So notice our fundamental theorem of calculus then has all the earmarks of Green's theorem, and it has all the earmarks of the two-dimensional divergence theorem. Accumulating quantity, whole is the sum of the parts, integral over the interior, the integrand is the associated density. It's a shameless ripoff. I mean, it came first. Okay, so the others are ripoffs of it. But from this point of view, the way I'm presenting it here, it's like we're just stealing straight out of Green's theorem. Is that cool? Okay. Okay, now a couple of takeaways. So first takeaway, this derivative thought of as a density. Let's think about mass for a second. What does mass density tell you? Mass density is telling you this total amount of mass that you're interested in, the density is telling you where it is. Where is it actually sitting? With the densities higher, that means that there's more mass in that general vicinity. If the density is lower, that means that there's less mass in that general vicinity, right? I mean, that's kind of, in some sense, density's job is to tell you how much of it is where. All right, well, I claim the derivative does that here as well. The derivative is telling us how much of the total change that you see over the interval, how much of that is happening in a general vicinity. So it's actually really geometrically satisfying. Let's look at a point along in here. The derivative is significantly positive. Let me just, for language purposes, say large. Derivative here is large. Derivative being a density telling you how much of the stuff is happening in that general area. My interpretation of this derivative being large is that there's a lot of change happening here. Yeah, of course there is. Look at it. Right? Look how much the function changing a lot along in this part of the domain. Now, just by contrast, you look over here, point like this, derivative is 0. 0 being the density is telling us that, this change that you see, the overall total change that you see on this interval, it's not happening here. Which again, right, of course, you can see it right there in the picture. It is not changing there. Right? So that's what densities do. Densities tell you where the accumulating quantity is happening. So a kind of combining an overall perspective on this is as follows. And again, we've got a certain amount of change that happens over this interval. How am I going to compute how much change that is? Well, I've got a formula. It's f of b minus f of a. That's computed at the points b and a. So I compute this accumulating quantity at the endpoints. I compute this accumulating quantity on the boundary. But that is absolutely not where it's actually happening. Where is it actually happening? It's happening in this is where it's actually happening. Right? That's where the change is actually occurring. And now I think that in this case, looking at the change being our accumulating quantity, I think it's really satisfying. If I make the outrageous suggestion that something that I compute on the boundary is actually happening in the middle, in the interior, of course it is here. Right? Change, I can see it changing. That's where it's changing. Perfectly relatable. Nothing creepy, nothing mysterious. Right? And why I like this is if you're willing to buy and digest this idea that things that you see on the boundary can actually be happening in the interior, then you might be more willing than previously to buy what I was talking about here. Because after all, that's exactly the statement that I was making here. Creepy though it seemed at the time, right? But my big outrageous suggestion here was that boundary circulation, right, that we measure on the boundary, I made this weird suggestion that it's actually distributed over the interior. Seems very surprising. After all, I computed here. I computed on the boundary. What do you mean boundary circulation's happening in the interior? Well, I mean it in the same sense. In the same sense that here, the thing that I compute on the boundary is actually happening in the interior. So to the extent that you're willing to buy this story, I hope you will, think about the compare and contrast between this and what we were just looking at, several pages back with Green's theorem and, circulation being in the interior and et cetera. And I think looking back and forth between those, the amount of comfort that you have with this might help translate to give you more comfort with the claim I was making before. All right, now let's throw some numbers at it. Now this is a kind of a silly example. You know what? I changed my mind. We're going to come back to this in a second. Let me draw the analog of this picture here first. We'll do some numbers in a second. Okay, so I can see right here in the picture that, hey, that's where the change is actually happening. Of course it is. And there's clearly no change happening there or there. And furthermore, the derivative points to it, right? The derivative being 0 here tells me there's 0 change happening there, etc. Okay. All right, so let's look at this picture here. We have a rectangle, solid rectangle with a boundary rectangle. Okay. And let's talk about circulation. Right? We're going to be talking about Green's theorem here, and sort of trying to visualize and make an interpretation of Green's theorem. So circulation, how do we measure circulation? Well, that's a line integral that we compute around, counterclockwise, or however you want to say it, around the boundary. So obviously, circulation, it's measured on that purple curve because, well, that's the formula, explicit formula for circulation. Integral on the boundary. Okay. Now, I'm going to claim this circulation is positive. I think this is not too hard to believe. If we look on this edge, notice that the field is that way, but my dx vectors are that way, and those are orthogonal, and so f dot dx is going to be 0 on that whole edge, and we can kind of ignore that. There's no circulation that's going to come up on that edge. And likewise, on this edge here, again, the field is like this, and the dx vectors are like that, and again, perpendicular, again, 0 dot product. Okay. But on this edge, the field is like that, right? The dx vector is like that, and f dot dx, well, these two vectors are pointing the same way. This is going to be positive. And adding up over that whole orange line segment, there's going to be a significantly positive vector line integral along this orange edge. But then I also need to look at that edge where, again, the field is like so. The dx vectors now are like that, again, counterclockwise, following the rules. These are pointing exact opposite directions. This dot product is negative. So on the top edge, we're going to get a negative contribution to the circulation. So all together, just, you add it up, the actual total circulation, there's a positive and there's a negative, and a little bit of a tug of war going on between the positive and the negative. Then just notice the vector field is longer down here at the bottom. So there's a bigger positive and a smaller negative. So this adds up to positive. Okay. All right. So where is that circulation happening? Green's operator will tell you. You can compute Green's operator, and it'll be positive in some places and it'll be 0 in some places. And we can see right in the picture where that will be. Because after all, if I drop a dead leaf right there into the flow of whatever fluid this is, and what's going to happen? Well, the water is kind of pushing on it on that side. That'll kind of push it clockwise. It's also going to get pushed on this side. That's going to push it counterclockwise. These two field vectors are the same. It's going to be pushing same amount in opposite directions. This leaf is not going to rotate as it flows downstream. This leaf is just going to kind of go straight. No rotation at all. Likewise, down here. Now it's being pushed harder because there's a longer field vector on that, so it's going to be a greater sort of force, if you will, to trying to turn this clockwise, but it's also going to have a longer field vector and thus a greater, if you will, force trying to turn it counterclockwise. Again, same opposite directions, again adds to 0. So this leaf isn't going to rotate either. This leaf is just going to kind of go straight along. But what about this leaf right there? Well, that leaf is going to be, again, pushed on both sides. This field vector is going to be trying to turn it clockwise. This field vector is going to be trying to turn it counterclockwise, but the one on the bottom is stronger. Longer field vector, more rotational force, as it were. And so what do you expect this leaf to do? I expect this leaf to be kind of rotating counterclockwise as it flows straight downstream. Everybody buy it? So you can compute this out with Green's operator, and up here, Green's operator is 0. Down here, Green's operator is 0. But in this region in here, Green's operator is positive. So what we can algebraically compute with our circulation density points right to where the circulation that we measure on the boundary is actually coming from. Boundary circulation is coming from this gray region. That's where it comes from. That's where you might say that's where the rotation is actually happening. If you drop a bunch of leaves, take a whole fistful of leaves and toss them into the river here, right? And what you're going to find is that there's a bunch of boring leaves on the top and the bottom that are not rotating at all. And then in the middle, it'd be really cool, and all these leaves in the middle would be kind of rotating as they go along. Does that make sense to everybody? All right. Okay. Likewise for divergence here. So again, there's going to be a total amount of divergence. Total amount of flux. Excuse me. There is a total outward-oriented boundary flux. That's a computation, and you could make a case here. I argue that the total outward-oriented boundary flux here would be positive. Think that through. It's a nice exercise. You just got to think about on each of the 4 edges, which direction is the field vector pointing, which direction is dx pointing, what's the nature of that dot product, positive, negative, or 0, and then just kind of compare the pieces and see who wins the tug of war. So you're going to get a positive flux here. Is there flux happening here? Nope. Vector field's all constant over here. There's just as much flux in to this green region as there is out of this green region. There's no net flux for this green region. Likewise, over here or over there, there's less flux in, there's less flux out, but again, the same amount of each, and again, they balance. But in here, if I look at that green region, there's just a little bit more out on the right-hand side than there is in on the left-hand side, because the field is longer on the right, shorter on the left, right? And so this is where all the flux that you see on the boundary, this is where it's happening. It's happening here in this gray region. And again, divergence will point right to it, and you can compute the divergence in all these places, and you will get divergence equal to 0 there. Divergence is 0 there, and the divergence will be positive in there. So now one last little quick take on how to think about this. And again, it seems a little bit weird to attribute stuff happening on the boundary to stuff happening on the inside. But now just real quick, what would the flux be if the whole field was just like it is in this green region? Imagine this green region being the whole vector field everywhere. There would be no flux. So this green region gets no credit for creating flux because it doesn't, right? It by itself copied sort of everywhere across there, no flux, right? But if you were to follow this pattern here in the gray region and have the vector field just continually getting bigger and bigger, lots of flux. So this is where that flux that you measure on the boundary, this is where it happens,
So like the net flux, is that all caused by changes in the interior? So
Yeah, that's right. It's the specifics of how the vector field is changing, but yeah, I mean it's complicated, right? You got to think there's a lot of details involved, but yes, what the flux is, what the vector field is doing over here is what is directly causing the flux that you measure on the boundary. Yeah. Okay. See y'all later. Have a good weekend. See you on Monday. Oh, real quick update on the exam. I am 3 of 5 pages done with the grading of the exam. My goal, not a promise, but a goal, is to get the grading done by tomorrow. Hopefully. I'll email you when I have it done. See y'all later.
Thank you so much.
Yeah, no worries. Have a good one.